My name is George Deloyen. I'm a CEO of NIS, Nanotech Industrial Solutions. And today it is my honor to introduce our webinar host, Professor Reshef Tene. He's a member of Israel Academy of Science and Humanities and Academia of Europea and a recipient of numerous honors and prizes. This year, Professor Tene was awarded the prestigious Emmy ET Prize, and he received it from Israel's Prime Minister Benjamin Netanyahu. Professor Tene is well known around the world, and it is very interesting to know that the future professor was born in kibbutz. For those who don't know what kibbutz is, it is like a collective community in Israel. In 1986, he received his PhD from the Hebrew University of Jerusalem and joined the Weizmann Institute of Technology in 1979. I hope I'm all correct with the numbers, Professor. And I'll continue. So in 1992, Professor Tene and his team discovered novel inorganic nanomaterials, nicknamed inorganic fullerene-like structures, with a quasi-spherical shape and inorganic nanotubes. And since then, Professor Tene became a pioneer and world leader in this field. He published around 300 original papers, and his nanotechnology is protected by dozens of patents. Professor Tene research led to the establishment of several companies, among them is Nanotech Industrial Solutions, which holds an exclusive license for his nanotube structures. Professor Tene was the director of the Helen and Martin Kimmel Center for Nanoscale Science, director of the Schmidt-Mineura Center and Supermolecular Architectures, and Drake Family Chair in Nanotechnology. Today, Professor Tene is now a research emeritus professor in the Weizmann Institute. So I'd like to welcome you. Thank you very much, Professor, to joining us in this webinar and running this webinar for us and all participants all over the world. And the stage is all yours. Thank you very much.
Thank you very much, George. It's a pleasure to give this webinar. And I'm very pleased. Actually, it's my first webinar. I gave hundreds of invited talks all over the world. And this is my first webinar. And I'm very glad to do that. And I'm very glad to host all the people from all over the world with great enthusiasm. And I hope you will enjoy my short presentation. And let's start moving. So how do I move my slides? Okay, so you see the introductory slide. You can see the difference between the color of my hair as in the original, in the picture shown in this slide, and my own hair now, which is a bit whiter because it was taken 7 or 8 years after this original slide. So let me go directly into the subject matter. So this is actually a collaboration. This whole entire enterprise is basically a collaboration between the Weizmann Institute. You see on the left-hand side the picture of one picture from the beautiful landscape of the Weizmann Institute. It's very greeny place and very beautiful campus. And on the right-hand side you see the NIS symbol. And this presentation and this work to a large extent is a collaborative work. On the left side you see all the foundations that contributed to my capability to finance these projects, and I acknowledge them with great thanks. So let me start by showing this slide. This is actually the fundamental slide that shows why graphite, which was the first material to form fullerenes and nanotubes, why graphite would form these structures. So if you see my mouse, you see that graphite is made of lamella. You can consider graphite like a deck of cards. And each card consists of hexagons of carbon. And you see that each carbon atom is bonded to 3 neighboring carbon atoms. So this is a picture that is relevant to the bulk material. But when you go to the nano, you have more and more atoms, carbon atoms, on the edge, on the rim of this structure, which are basically have missing bonds. Actually, so instead of having three carbon atoms, they are only bonded to two carbon atoms, and consequently, their energy is much higher, and they aspire to get rid of this extra energy. And the way for them to do that is to fold either into a zero-dimensional structure like that, fold and seam, or into a one-dimensional structure, which is called carbon nanotube. So this is the famous C60, which was discovered by Kroto and Smalley in 1985. They were awarded the Nobel Prize in 1996 for this great discovery. And then Ijima in 1991 discovered the carbon nanotubes. And then in 1993, he discovered the single wall nanotube. So the concept is very simple. You take a material which is made of like a deck of cards, namely very strong bonds within the layer and very weak bonds holding the layers together. And by this anisotropy, you actually force, by taking these nanoparticles, making this graphite into nanoparticles, you force them to fold and seam into such structure. So once I saw these papers popping out, I had immediately in my mind the idea, or immediately in few months, the idea that this is not unique to carbon only, but this should occur also in other layered compounds. And the example that is shown here on the screen is tungsten disulfide or molybdenum disulfide. So this is again a layered structure material. It is made of layers of, here you see the tungsten atom, here you see the yellow sulfur atoms, and you see that the layer is complete by having three atomic layers, sulfur or tungsten or molybdenum sandwiched between two layers, outer layers of sulfur. So this is one layer. The second layer on top is about 6 angstrom above it. And again, the interlayer forces are very weak. But if you think of what happened with carbon when it was brought into a nano dimension, you grasp immediately the concept that in these layers, they will not be stable as such as a planar form in the nano dimension. So if we look now into this from top, from here, from the C-axis, from top, on one such layer, we see that the molybdenum is bonded to 6 sulfur atoms in the bulk, but only to 4 sulfur atoms at the edge. And so is for the sulfur. The sulfur is bonded to 3 neighboring molybdenum atoms in the bulk and only to 2 molybdenum atoms on the surface or on the rim. And the consequence of that is that if you heat it to high enough temperature, this structure will not remain flat, but instead will try to seam. And the seaming is simply by folding and combining this molybdenum with this sulfur atoms and with this sulfur atom. So here you have a picture of this hollow closed structure. Basically, you form a hollow closed structures. Now, you know that in chemistry, hollow space is not something that the chemistry favors. But in this unique case, the nanostructures prefer to have a hollow cage structure, as you see here for the tungsten disulfide or molybdenum disulfide nanotube. And this has been clearly indicated, and you see now TEM on the left, TEM, transmission electron microscope picture of such nanoparticles consisting of about 15 or 20 layers of tungsten disulfide. Each fringe, basically the electron microscope is a 2D casting, 2D reflection of a hollow closed structure of tungsten disulfide. And if you tilt these nanoparticles in any direction, it will always be seen like that. So it's a hollow closed structure of tungsten disulfide, which is made of several layers. And I won't go into the details why it is like that exactly and why it's so different from C60. C60 is made of precisely 60 atoms of carbon. And here you have hundreds of thousands, if not millions, of tungsten and sulfur atoms. So it's much larger. The whole size of these nanoparticles is about 250 angstrom, 25 nanometer, or even larger, and it counts many, many atoms of tungsten and sulfur. And it took us many years to come to the possibility to see these nanoparticles in a unique phase. So basically what we see here is that after large effort, we were able to find the conditions or study the growth mechanism, the chemistry of the growth mechanism to such an extent that we can produce pure phase of these nanoparticles. Now remember, this is a nanoscale phase. This exists only in the nano, and no materials like to remain in nano, and if you heat it up, it will always go to the macroscopic nanoparticles, which is a flat surface, flat platelet. We call it platelet. Many, many layers like arranged like a deck of cards. But in this metastable phase, in this intermediate temperature, we know how to produce these materials now in pure phase in large quantities. And once you can do that, you can study all the properties of this material and find the interesting ideas about this material, because they are very different from the bulk material, as you will see in a minute. So here is another demonstration of, as I mentioned to you, there are these spherical shape nanoparticles, hollow nanoparticles, which we call fullerene-like. They are not fullerenes like C60 carbon, but they are fullerene-like. And there are the nanotubes, multi-wall nanotube. So again, a TEM, a transmission electron microscopy picture of one such nanotube. You see the many layers. You see how beautifully they are arranged in a like a wrapping of one layer on top of each other. So it's really a concentric tubular structure. And each fringe, each black line is basically one layer of tungsten disulfide. So you have about 10 layers or maybe more of layer growing bigger and bigger. And so this is the nanotubes. And again, slowly by slowly, we study the growth mechanism of these nanotubes, and we can now produce them in substantial amount as a pure phase. And this allows us to study their properties in a very precise or very punctuous way. So this is, as you know, this is the first demonstration of a nanotubular shape, which is not made of carbon. And this is why it received so much attention, because now we know how to synthesize nanotubes basically from many, many layered materials with a shape of a deck of cards. And we can make now a lot of these new nanotubes from a variety of chemicals which have the shape of a deck of cards, layered materials. So this is a great lesson in inorganic chemistry, and indeed it is considered as a major revelation in inorganic chemistry, which goes now to any textbook, in modern textbook in inorganic chemistry. And here you see a beautiful picture. So you see in the previous picture, I showed you the nanotube. In the previous slide, you saw the nanotube, but you couldn't see the details up to atomic scale. But since about 15 years, we now have the new generation of transmission electron microscope, which can see atom by atom. And this is the picture taken by my former student, Maya Barsadan and Lotta Huben. And you see here now clearly, here the red circles are the tungsten atoms, and you see each and every tungsten atom in a layer of a nanotube. So here you see the tungsten atom, and here you see the sulfur atom. And so we now can study their structure to the finest detail, and we can see that indeed these are tungsten disulfide nanotube. And you see the tubular, you first see the tubular structure, and you see how nicely and how perfectly this layer are stacked together to form this tubular form. So now let's go a little bit into the properties. I told you that once we learned how to synthesize these materials in large quantities, we can now look into their properties. But in fact, because each nanotube is a bit different from the other one, and each fullerene-like nanoparticle is a bit different, it's actually our aspiration is to learn the nanotubes one by one and measure them precisely as we can and understand their properties. So here is the mechanical properties of individual nanotube. And you get the impression, immediate impression. You see this is the work of my former student, Yifat Kaplan-Ashiri, Dr. Yifat Kaplan-Ashiri, together with many people, Gotthard Seifert, Professor Gotthard Seifert, Professor Daniel Wagner. We all worked together to come up with this beautiful paper, which was published in PNAS in 2006. And you see how the nanotube is flexible and does not break. Simply, if I stick in the microscope this nanotube to a tip, and she compress it against a silicon wafer or some other surface, and she get this beautiful folding nanotube. So the nanotube is not breaking, it's folding. And this is a very important finding, because now we see that we have a material which is both very strong and very flexible. And this is quite unique, as you'll see in a minute. So here is, I don't show the video slide, the video of this movie, of this slide, which was prepared by Gotthard Seifert group in Dresden. But you see, once you have a single nanotube and you can characterize it, you can also generate it on a computer. And once you generate it on the computer, you can calculate the properties and you can come up with answers and compare them to the experimental results. And that's what we did. So Gotthard Seifert calculated the failure mechanism of this nanotube. So he actually pulled these nanotubes by moving to up and here down, and you see how the tensile stress of this nanotube leads to a failure of the nanotube immediately at the center. And this was really the same mechanism that we saw in our electron microscopy analysis of this nanotube. So basically we found actually, I won't go to the detail, but we find two kinds of nanotube, type 1, type 2, it doesn't matter. What is important is that then type 1, they are narrow, very narrow. They are probably 30 nanometer. They are very small. They have a hollow core, and they fail like a swording tooth. So namely, all the load that we apply on it and is actually taken by the outer layer, and they failed up to a force of about 6 or load of 6 gigapascal. So this is the mechanism that applies to this narrow nanotube. However, the thick nanotubes, as you see here, have a lot of defects, and these defects pin the layers together so that if you pull them apart, they actually, all the load is taken up by all the layers, and consequently you get to much higher forces. This is the red curve here, much higher force. So you can pull them apart and they would not break until 20 gigapascal. Just to give you an imagination, 20 gigapascal is equivalent to 20 tons applied on your nail, So it's a very, very big force, and yet they do not fail, which shows that these materials are extremely good for a variety of applications, which you will see in a minute. So here is an example. The video should come somewhere here. Let's see if it works. I think that there will be a video here. Let's see if it works. Yes, so this is an experiment done by Yifat Kaplan-Ashiri, Dr. Yifat Kaplan-Ashiri, and you see the two edges or the two tips. The nanotube is bonded to two tips, and you see as we press them together, the nanotube falls on itself, but it doesn't break. And this gives a new dimension to this nanotube. Not only they are strong under tensile stress, but they're extremely flexible. And if you know the mechanics of materials, usually you fail you see materials which are very strong and robust, like ceramic, but with very low fracture toughness. If you bump into it, if you give it a hit, it will break. On the other hand, you have materials like rubber or plastic, which are very foldable, very flexible, and but they are very weak. They are not strong. And so here you have a material, the nanotube, which is both strong and flexible. And that is great for a lot of applications, because if you put a little amount of this nanotube in a polymer, you get a material which is both very flexible and very strong. And that's something that I will show in a minute. Okay, so I'll go back to the slides. Okay. So here's the slide. Now let me go to the next slide. So let me go first to the first application, which is actually the most relevant to NIS, to Nano Industrial Solutions, the company, and to its daughter company, Nanomaterials. So there are two known mechanisms, very well old known mechanism of lubrication, sliding and rolling. Here is a picture taken from the tombs of Tutankhamun in Egypt, which goes back 3,000 years ago or so. And you see this beautiful sculpture taken by thousands of slaves. Yet there is a person here standing here pouring water or oil below the surface of this sliding slide. And this facilitates the sliding of this sculpture by a big, let's say by a factor of 2 at least. It reduces the force that is needed to move this sculpture from one place to another. You know that they sculptured very huge sculptures and patterns and stones, and they slid them over from large distances to the building place. And here you see how they did it. It's a beautiful show demonstration of the sliding friction mechanism. On the other hand, we also know another friction mechanism. This is the rolling. And this is actually a picture which was also taken from Egyptian documents. So basically what you see here is a ship, and you see these two gentlemen putting logs below the ship, and the ship is progressing, sliding. The logs are simply rolled and providing a rolling friction. And these gentlemen provide the logs to these people that push this under the ship. And of course the slaves that push it together. And we have also evidence for the Maya. The Maya built the pyramids in Peru and in Mexico. Also you see these logs here, which facilitate or lubricated the sliding of this, or the movement of these large stones from their mining place to the building place. So these two mechanisms, the sliding and the rolling, are very well known in modern technology. And here we have an example of how we do that for one single fullerene like nanoparticle. So imagine yourself now that we go from the Egyptian time or the Maya time, and we are now modern with our modern tools. We can look on one nanoparticles, which is 100 nanometer in size, very, very small. So you have to have a very good microscope in order to see it, let alone manipulate it. But we manage with a very articulated technique to stick this nanoparticle on the edge of the wafer, and then come with a tip and roll it. And you'll see it here in real term. You see it within the microscope in low resolution. And if you go to very high resolution, so you see now the nanoparticle, and you see there is a red spot, and you see that in the middle, in the beginning of the experiment, actually in the beginning of the experiment, the red spot was here, afterwards it was here, and afterwards it was here. So this means that the nanoparticles rolled under the load of this cantilever. So we have a tip with cantilever which loads vertically on the nanoparticles and at the same time pushing them, shearing them, and we see the rolling friction. So imagine for yourself now, we see the rolling friction like the Egyptians saw many, many years ago, but now we see it on a single nanoparticle in a very clear fashion, and we can calculate the friction coefficient and show indeed this is a very good and very efficient lubrication mechanism. And we studied this in great detail. It was published by Ofer Tevet was the main student to carry out this research, again in PNAS in 2011, and you see the three main mechanisms of the lubrication. So rolling is the one, sliding, when you increase the pressure to 1 gigapascal, which is equivalent to 1 ton or 10 tons, I think. No, I think 10 tons on your nail. It actually slide because there is no way that the nanoparticle is already a little bit deformed, and there it slides between the two surfaces. And once you apply very large pressure or load, you get the exfoliation of the nanoparticles, and these exfoliated nanoparticles lie on the surface and provide extra lubrication to the surface until they are consumed, chemically consumed. So this observation was very important to verify the lubrication mechanism and to vindicate that these materials are very good lubricants for a variety of purposes. And the applications are numerous, as is worked out by NIS and Nanomaterials, and they are actually have commercialized and mass produced these materials now in many, many tons, and different kinds of lubricants, including oils, greases, and metalworking fluids of emulsions of different sorts, which can be used by the manufacturers of many others, many things. So I won't go to the application. George can elaborate on that afterwards. I want to show you something else. If you go to very low, here we demonstrate something completely different. We show how endoscope go to the body of a human being, because there is a need also for lubrication in medicine. When you have, ambulatory surgeries now are very popular. If you want to push a catheter or stent or endoscope into the body, you have to have a small constriction, either a natural one that you have on top or in the bottom, and you use it to insert endoscope, catheters, stents, etc., etc. And we tested this lubrication by having a simulator. We built a simulator with a very soft ring which simulates the human tissue, and the endoscope, the metallic tube that goes through this ring here in between these two metal plates. And using an Instron machine, we can quantify the pulling force of these slides of this endoscope, and we find that in fact, if you consider the procedure that is being used in the hospitals, they use a lubricant called esarcaine, which I won't go into detail. You see the attraction force of this endoscope from the rubber is almost 9 Newton. But when you lubricate it with better and better lubricants of our production, so we can go for different kinds of lubricants, and the most superior one is the one with molybdenum disulfide or tungsten disulfide with a little bit of rhenium inside, and you see how much we cut the friction by a factor of 4. And this is very meaningful because this procedure are ubiquitous in hospitals, and patients are suffering a lot by insertion and extraction of this endoscope from the body or catheters from the body. And if you can lubricate this process, you can get a much better improved medical treatment. And this is why the urologists and cardiovascular specialists were very enthusiastic to see this kind of work. So this is a major medical application which we have continued to work, but we have not finished yet. And this is another demonstration that if you use rhenium doping of our nanoparticles in a very precise way, and it's extremely difficult experiment. It's extremely difficult to put rhenium in the measured amount into these nanoparticles, hollow nanoparticles. We get friction, which is so low that is under very high pressure of 1.68 gigapascal, which is barely found in reality. And yet we can reduce friction from lubricant used today factor of at least 2 or 3, as you see from here to here. And this is true for many kinds of experiments that we did. So I won't go into details, but I would like to go now to the last part of my talk, and this is the composite. And we studied variety of composite. I won't go into that, but I will show you some examples. And one example is this nanotubes, which we impregnated into polylactic acid. Polylactic acid is one of the main polymers, biocomposite polymer, which is used nowadays in medical procedures, in many medical and not only medical, packaging, food packaging, and many applications. So now we add very little. We put here 0.25, 0.5, even 0.8, up to 0.8. Usually 0.25 to 0.5 is the optimum. And you see that we start, this is the stress strain curve. So we take the nanotube, the polymer, we pull it from two sides, and we measure the force that we apply and how much it can elongate before it breaks. And it fails. Actually, it starts to show failure here, and eventually it breaks at this point. So you see the force goes down dramatically. And this is the curve, the typical curve, the strain stress curve of the polymer. And you see that this is the knit polymer, PLLA, which is very weak. And when we add nanotubes, we can go gradually up until we really make it very robust. Not only it became strong, if you now integrate, if you simply take the area under the curve, this is the force that is required to break this polymer. And the force here, if you take this integral area, the area under the curve, compare it to this, or even to that, you see that addition of a very small amount of these nanotubes has reinforced this polymer dramatically. So that's a real important finding, because the finding here is that first, it's very easy to disperse this nanotube into the polymer, which is unprecedented actually, and you don't find it in other nanoparticles. And secondly, it reinforces the polymer dramatically. And one third property, which is very important for any application, is these nanotubes are found to be non-toxic. So they are completely biocompatible. At least so far, there have not been any in situ experiment yet on human being, and it will take time until we can do that. But we are getting closer to being able to show that these materials are very useful to many medical technologies. And that's why there is so much interest in these materials also from this industry, but not only, because polymers are used everywhere. And I want to show you few examples. So here you see a recent paper which we published jointly with, the work was the student Hila Shalom, and jointly with Dr. Noah Lachman from Tel Aviv University. And what we did 3D printing of a product, or basically of a prototype of a product, based on this PLLA, the same PLLA, the same biocompatible polymer with the same amount of nanotube, 0.5% or even less. And you see, I won't go to the details, how it goes through the extruder, and then it goes, the filaments that are produced by the extruders go now to the 3D printers. And here is a picture of an artificial air that we could make from this mixture of or composite of polymer with the nanotubes. And you can see it. I show it here on the. I don't. Here you see it in reality. So this is an air that artificial air that has been produced. And of course, the idea is not to produce an air, but the idea is to use it, for example, for different replacement of human body. When you have unfortunately, there are many car accident, and if somebody breaks his leg or somebody breaks his bones somewhere, we can potentially replace them at least for a few months until the bone is fully recovered naturally. So that's the hope. And here I show you the potential of this one of this nanotube. And here is another demonstration published recently by Dr. Stojanovic from Serbia with her student Simic, Dr. Simic, Mr. Simic, and me jointly in Composite Part B. And this is a publication where they actually produced a sheet of composite, reinforced composite, where they took epoxy with aramid fiber, and they made a fabric, aramid fabric. And this aramid fabric, this is the neat one, which is yellow, and then they added up to 0.3%, or even, no, this is 3%, this is 0.3. So you see that they added the nanotubes, and not much. You don't need more than 0.5% or 1%. And then they did a test, a shooting test. So they have a laboratory, and here you see the gun, and you see two high-speed cameras to show you the event of the bullet going into the sheet. And here there is a simple comparison between the two sheets. So this sheet is the neat sheet without the nanotube, and you see that the bullet, this is the back of the sheet, and you see that the bullet easily penetrated through the sheet. While when we added only 0.3% of the nanotubes into this sheet, the bullet did not penetrate. Now this is a magnum bullet, magnum bullet. So it's a pistol. It's not a rifle. It's not a gun. So the bore speed is much lower than a real rifle. But for policemen, it's good enough to protect policemen. It's good enough to protect even soldiers, depending on the distance from the shooting area, distance. And here you see the pictures of the high-speed camera. So you see that here you start it here. The bullet goes from the front, and here there is a heat wave developing, and you see that the bullet is actually stopped here. It does not penetrate through the sheet. So here you demonstrate beautifully that by adding such a small amount of this nanotube, you provided a very solid protection of, let's say, human being by who wears this protection jacket, self-defense jacket. And here you see some other details which I won't go in detail, but if you go to the NEAT, just show you, this is a thermal imaging with thermal camera. So there are, I showed you two cameras, one high-speed camera which shows the bullet and the system, and one thermal camera which measures the temperature. And you see that the temperature in this case, in the NEAT, went down very fast, because there was almost no friction between the bullet and the aramid fabric. While when the nanotubes were in, the temperature did not went out very fast, because there was a lot of friction, a lot of interaction between the bullet and the fabric, and consequently the temperature went down much slower. So I think that with this I conclude my short presentation. I focus mainly on the first principle, how we synthesize these materials and how we measure some of their properties. I didn't go to many other details that exist. And eventually I showed you some very novel applications. I hope you enjoyed this slide. And my last picture is my group. Actually, it's not my current group. It's my group about 5 or 7 years ago. And you see me here in the center with my student and collaborators. So this student actually provided all the know-how that we have in order to be able to study these materials in great detail and get the applications right on. So with that, I would like to conclude my webinar and thank you for your attention. And I'll be very happy if you have any questions on this lecture. Thank you very much.
Thank you very much, Professor Rashid Tanner, for a very interesting presentation. Yeah, we have a great attendance from all over the world, and we already have several questions to go through. Okay.
So you choose perhaps.
Say it again?
George, you choose the question that I should address.
Right. Yeah, the one that we're not going to be able to address, we will definitely answer within 24 hours via emails. So there's one question, first question, what is the mass percentage of nanotubes were in the PPLA filament used for 3D printing?
So actually, if you look on the weight of the nanotubes, they're about 3 to 4 times heavier than the polymer itself. And so if you take it by volume or by atomic percent, let's say 0.5% weight percent means about 0.1 or 0.2 at the maximum atomic percent of volume percent. So that's a very little amount of nanotubes in the polymer, and yet you get such a reinforcement, almost unbelievable reinforcement.
Okay, so what was the percentage approximately, mass percentage, do you remember, on that year 3D printing piece?
Oh, yeah, again, it's 0.5%.
Oh, 0.5%, okay, thank you.
0.5%, it's always, the maximum is 1%, but it's always closer to 0.5% weight percent, which means atomic percent is about between 0.1 to 0.2.
Right. Okay, next question. By any chance, do you have compared this material with the graphene oxide systems?
Yes, I'll be glad to answer that. It's a long question. It's a long answer it's a long answer. First of all, you must understand that the amount of work dedicated to graphene and carbon nanotubes is so huge that almost any property has been measured and known, or at least on the way to be known. With regards to these nanotubes, first of all, they are much more complex in structure because they are not single layer. They are not, unlike graphene or unlike single wall carbon nanotubes, they are multi-wall. They are always multi-wall. It's very difficult to make them single wall. We know how to do that, but we cannot make it in large amounts. It's very difficult. And if you compare them, carbon nanotubes, for example, the Young's modulus, the mechanically, the carbon nanotubes, the Young's modulus of carbon nanotubes is 1 terapascal. And it's about factor of 5 or 6 larger than tungsten disulfide. So basically, and perhaps factor of 4 larger than molybdenum disulfide. Molybdenum disulfide is a bit stronger than tungsten disulfide. So you would think that carbon nanotubes are very advantageous compared to tungsten disulfide, but it's not. The reasons are simple. First of all, carbon nanotubes and graphene have the problem of pi staking. This is a very serious issue. They agglomerate very fast. They are very entangled. They are very difficult to disperse. And for example, if you try to disperse 1 or 2% of graphene in a polymer, you are stuck with instead of having a liquid or molten polymer, you have a chewing gum. You have a plastilina. It's really very viscous. While when you add these nanotubes or these fullerene-like nanoparticles to the polymer, the viscosity goes down. And that's amazing by itself. We are submitting a paper on this topic now, right away now. We are about to publish a paper on that. And so this is a major advantage of the nanotubes and fluorines from tungsten disulfide, that the viscosity does not go up, it goes down actually. And then it's so easy to mix it. Now think about large scale application when you have a pot of 1 ton where you want to mix these nanotubes with how much energy you have to dispense in order to mix them, the nanotubes evenly in the case of carbon nanotubes or graphene and these nanotubes. It's unimaginable, the difference. So they disperse very well, and even though they are 5 times, in theory, they are 5 times weaker than carbon nanotubes, basically engineering-wise, they are only factor of 2 weaker, not more, because we know how to synthesize them very well, and they are very strong and very robust. So and now if you have a polymer with, let's say, a strength of 50 megapascal, which is very high already for a polymer. Usually polymers are somewhere 20 megapascal to 30 megapascal. If you have a polymer like epoxy, it's 50 megapascal, and you reinforce it 20 times, the nanotube is at least 20 times stronger, at least, if not 100 times stronger. So what does it matter if it's 100 times or 200 times? It's important that the nanotubes disperse well in the polymer. It is important that their rheology is very good, namely they mix very easily, disperse very, very easily, and eventually they provide very, very good interaction because the sulfur atom at the edge of the nanotube provides a very good interaction with the polymer in many cases. So we have a very good pillar for reinforcement effect.
Yeah, thank you very much. That's very, very good information. Okay, next question. How to overcome agglomeration problem in nanomaterials during the storage and also in lubricating oils?
That's a very good question. I'm not sure that I am able to answer fully this question. We have to use surfactants. But just to give you, again, I want to emphasize that the difference between carbon nanotubes and graphene and these nanotubes do not stick very strongly to each other. Of course, they agglomerate. They will always agglomerate due to weak van der Waals interaction, but it's enough. If you have 1 million nanoparticles and they stick together, they form an agglomerate of 10 microns or larger, and you break them fairly easily, either mechanically with ultrasonic or with some other tricks. And if you add a surfactant, and we know, and we published several papers, and other people published, they disperse very well, and they don't precipitate. And I'm sure NIS can provide an even better answer. George, you can probably provide a better answer because your emulsions are stable, even in water, as far as I understand. And so I think that it's not fully, I cannot address this in full, but at least we know that they form stable suspensions.
Yeah, thank you very much, Rashim. I'll just add a couple of words to that. When you work with any solids which are not soluble but they're dispersible in any liquids, it's very important to use proper chemistry and proper surfactants to make sure that you make a homogeneous and stable suspension. It is not a straightforward or easy answer to that. Yeah, we do produce oil dispersion like 50% concentration and water dispersion 50%. But you also always need to remember that these products are dispersions. It's a two-phase products. Is a solids in liquid phase. And since we're present on Earth where we have a gravity, eventually, like we're talking about longer period of time, you may see some separation. You may see some thin film of on the bottom with the time. But it's very important what kind of sedimentation you have. If it's a sticky polymeric, it's not good because you're not going to be able to bring it up. If it's it's easy to actually to bring it up by mixing. It's very good. Most of our solution, they're stable for a year plus, which is actually really considerably super stable. Uh, but the time is also a factor here, and density gradient is very big impact here as well. But anyways, we're gonna go through the rest question. There are a lot of questions I can see. Um, uh, what would be the process? What would be the process to add a small percentage of IFWs to and or nanotubes to a commercial PLA material?
I,
Any?
I guess we use 2 or 3 different procedures. We use casting, namely that we prepare a solution and we dissolve or disperse the nanoparticles or the nanotubes in polymer and the solvent, and slowly we evaporate the solvent, and we have then a film forms. This is one way. The other way is, of course, as I mentioned, through 3D printing. So you first have to prepare a mother filament by extrusion, and afterwards this extrusion, these filaments are being introduced into the 3D printer, and you can print it. So there are a number of ways, and that's not actually, these are not the only ways. We have used many other ways to introduce the nanotubes, and other research group have introduced different ways, either by melting together or there's a lot of methods there. I mean, if you have a thermoplastic polymer, you can melt it. If you have a thermostatic, you have to mix it with the epoxy resin, for example, and then solidify it. There are many ways, but it's quite technically it's quite simple, relatively simple technology.
Yep, thank you. Next question, very interesting question. And I think I lost it. 1 second. Okay, with the spherical tungsten disulfide particles, do they release sulfate or sulfur under high force exfoliation condition in aqueous dispersions?
No, the answer is no. They are very stable. Of course, if you heat them to above 200 degrees, I mean, in dispersion, in solution, you cannot heat them to 200 degrees C. But in air, if you heat them in air, they start to make sulfides and tungstats, of course, but at a temperature of about 300 degrees, actually even below that, but the rate is very slow. But in anaerobic atmosphere, namely in a polymer or in another matrix like metal or ceramic, you can heat them above 1000 degrees C, and they won't. Nothing will happen to them if they don't react chemically with the matrix itself. So we have shown already mixing them with magnesium and aluminum melts, and we saw similar effects to the one that I mentioned with the polymers.
Okay, yeah, I'll probably expand this question. So, for example, in example of let's say metal operation, metal cutting, and on the tip there could be a very high temperature where we're applying the load on the particles as well. There is on the tip very high temperature. Would that condition make sulfur get released?
Yes, the trouble is not so much the temperature as the ambient condition, the air, because you have air around you. And so if you work with a lathe that works at an inert atmosphere, you can go to much higher temperatures compared to air atmosphere.
Okay, thank you very much. We have a couple more minutes left. There are several questions. What is a partial charge on a surface?
The partial charge is negative. If you look on the zeta potential, if you measure the zeta potential, the surface charge of this nanoparticle, it's always negative. There are several reasons why this charge is negative. First of all, the sulfur, the outermost, you must understand that the surface is always sulfur in this case, and the sulfur is negatively polarized. So you have already some kind of negative polarization, dipole. But then, of course, also, because these materials are synthesized at elevated temperature, there will always be sulfur vacancies. Because if you take tungsten and sulfur, the sulfur is much more volatile than tungsten, and you remain with sulfur vacancies, and these sulfur vacancies induce negative charge on the surface of the nanoparticles. So in summary, these nanoparticles are negatively charged, and you see it very clearly in zeta potential measurement and in other measurements. Also, if you do electrochemical deposition or electrophoretic deposition, they will always be attracted to the positive electrode.
Yep. Thank you very much. Yeah, I think we have time for one more question. There was, let me just give me a second. So there was a question: what are the applications for tungsten disulfide in spherical and tubular form? What are the most common application for these two type of solids? And
So
I probably will add to that as well.
No, basically I mentioned them, both of them. I can go. There are many more applications. There are also potential application in optics and in electricity and in electrical properties, but I won't go to them. It's too long to go to this. But basically the most common applications now are the lubricants and metal working fluids, which are fully commercialized by NIS. And George can answer you in more detail. And the second application of the nanotubes, mostly of the nanotubes, is both in reinforcement of polymer, but at the same time, you endo this polymer also with very good lubrication property. And this is why it's so good for many, many medical applications, because you want to introduce a catheter into the body. You want it to be strong at one end, and at the same time go very swiftly into the body without causing lots of pain to the patients. So there are many applications in sport, even in cars or in aerospace. And I won't go to the details, but there are several applications already exploited in aerospace application.
Right. I'll add to that. Yeah, the applications are in an industrial applications. What we see and where we see the most benefits are heavy-duty industrial applications, like metal working fluid, mining application. We see like we're giving like a lot of benefits, and we see a lot of benefits of particles used in oil for gearboxes and reducing energy consumption in gearboxes. On a big dump trucks. We see applications in various applications, even in wire ropes. We see applications in metal working fluids, especially very interesting. That we see in a water-based dispersion, the performance it gives in water. That's really interesting because water we see performs from tribological standpoint of view better than oil. Of course, there are many other aspects of the lubricant besides tribology, but it's kind of mind-changing moment that the water just possesses right now such a high extreme pressure, has such a low friction and low wear. So applications are endless. And also coating is very good application we see. But very interesting thing we see about the particles, the harsher condition is the better particles work. So the more load you apply to the particle, the better it start working. So that's very important point as well. And you can go on our website on nisusacorp.com, and you can see various applications where you're posting, and we're constantly posting on LinkedIn many trials, field trials from all over the world. And I think that's it. We have more questions. I'm sorry if we couldn't answer all of them during this hour. You will see this webinar will be available on video as well. It's recorded, and it will be uploaded on YouTube as well. and it will be available for everyone. The rest of the questions, please send to info@nisusacorp.com. Any question that haven't been answered during this Q&A session, they will be answered personally through emails. Please give us some time for that. And Professor Rashev, I'm personally would like to thank you for this amazing presentation, for your time. It has been great to see you. I wish you and your family great health. It is very important during this time, and great health to everybody who participated in your families, absolutely. And thank you very much.